Let's do a few examples of calculating work for various processes. The important thing to remember when doing work calculations is that you should always start with the general equation for work. Okay, don't jump to the specific case until you're sure that it applies. And so the easiest way to do this is just start with the general equation and then go from there. We often have cases where the external pressure is constant, and the most common example of this is when we run a chemical equation. It's often in an open vessel, and so it's going to be whatever atmospheric pressure is that day. So it's pretty easy to calculate the work because we have our fundamental equation for work, for expansion work anyway, and since pressure is constant, we can just, external pressure is constant, we can just pull it outside the integral. And since we're integrating from V1 to V2, we can see this is just going to be the negative of the external pressure times delta V. As a simple example, imagine that a reaction liberates 1 mole of gas. In an open vessel. So an example of this would be if you mixed enough baking soda and vinegar to create 1 mole of carbon dioxide. So in this case, the work that would be done in pushing back the atmosphere is the negative of the external pressure times delta V. Well, in this case, you created 1 mole of gas, and you didn't have any gas at all, so delta V is just the volume that is occupied by that 1 mole of gas. And we can see, if we just plug in the ideal gas law, we know that the molar volume of gas is just RT over P, and the P that is applying for the gas is P external, so we can cancel that. So that would be equal to negative RT. Or if we wanted to plug numbers in here and get an answer in joules, it would be negative 8.314 joules per mole per Kelvin. We multiply that by the temperature. So if we were working, I didn't give a temperature, but suppose we were working at 298 Kelvin, we can see that this would be equal to a negative 2,500 joules. Oh, and I neglected to say that we had 1 mole of gas. So we had 2,500 joules per mole, and we have 1 mole of gas. So we'd have to do 2,500 joules of work, or the reaction would do 2,500 joules of work in pushing back the atmosphere. So that's how much work would be extracted from the system. So in this next example, we're going to do a reversible expansion of an ideal gas, and it will be at constant temperature. So we start off always with that fundamental expression for work, and then we start looking at how the particulars of our problem are going to change this equation. Well, we said it's reversible, and if a process is reversible, we know that the pressure of the system, P, and the external pressure have to be the same. If there's a non-infinitesimal difference between those two pressures, then the process is not reversible, it's irreversible. So because it's reversible, we can substitute P for P external. Okay? And you might even want to make a little notation when you're doing problems like this about why you were allowed to make that substitution. Almost like doing a 2-column proof in geometry. Okay, so that was the first piece of information we used. What can we do? Well, we can't do the integral unless we can change the integrand into a single variable. So we've got P and V. So what we need to do is put P in terms of V or V in terms of P. And we can only do this if we have a physical equation of state. Unfortunately, we do. We said it was an ideal gas. So now we can say that work is the negative of nRT over P, or rather over V, dV. Great. Well, it still doesn't solve the problem because now we have two other variables. We have V and T. We need one variable in the integral. And then we check and we see, oh, well, this is a special case. It's a special case where the temperature is constant. It's an isothermal process. So we can pull the T outside the integral. And of course, we can pull out the number of moles of gas, and R and T. All those things can come out of the integral. And so we're just left with dV. So we pull out the negative nRT. We've still got dV over V, and particularly we're integrating from V1 to V2, initial to final. And of course, we've got negative N RT, and then we take the integral, we see that it's going to give us a logarithm. And so we have the log of V2 minus the log of V1. So it's negative nRT log of V2 over V1. The important thing to remember is that we can only use this if the process is reversible and isothermal and it is done using an ideal gas. Otherwise, this expression does not apply. So we have to remember not to apply a specific case equation when it's not appropriate.